Hi, all, and welcome to part 4 of atoms. All right, we were talking about covalent bonds, and I promised that I would show you the different ways in which they are often depicted. And we had started with, on this slide, we had started with two hydrogen atoms meeting up with one another, and the electrons that are circling each atom. Once these two atoms get close enough together, they start to be attracted to the other atoms positively charged nucleus, and then you have them swirling around both of them. And this electron cloud with the two electrons in it um, keeps these two atoms closer together in what we call a covalent bond. So here are some other ways in which we can depict this molecule. So this is a molecule because there are two atoms participating. So it's now H with the subscript 2. If you just have H alone, that's a hydrogen atom, but this is a hydrogen molecule, two hydrogen atoms together. So perhaps the space-filling molecule is the easiest, so we can just take a look at it. So this is two hydrogen atoms side by side, right? And they're close enough together that they are sharing electrons. Okay, the structural formula, and the one you'll likely see the most, is the straight line between two atoms that are participating in a covalent bond. So you see it like this. You can sometimes see the Lewis dot structure, which really literally shows you the number of electrons here. And you can see 1, 2. And because they're between the two hydrogen atoms, sometimes that the structure can also tell you if they're close, if the electrons are found closer, circling more around one atom or the other. I'll tell you more about that in a moment. But as these are atoms of the same element, they will attract the electrons equally. They're found right in the middle. And then here's another electron distribution diagram. I kind of like this one too, because this looks weird when you first look at these intersecting circles, but it allows you to see that this particular electron here can be part of, right? Remember, they're not orbiting, but can be swirling around this one, right? And it can also, if you look at it here, can be swirling around that one. I'm sorry about that. And likewise with this one, right? This electron that I'm circling here, I'll change it to green, can find its way to orbit around this one, not like a ring orbiting, but it can be found in the orbital all over and around. And this is meant to signify, erase it so you can see it again. This second is meant to circle, is meant to signify that this one can also come down and be around this one as well, right? Just all over the place, right? Found in, you don't know where, but somewhere in an electron cloud, in an orbital that we've defined as 1s. Okay, so that's another way of looking at it. So if you don't see it through what I drew, just take a moment and draw it with your own pencil why they would do these intersecting circles as they do. Okay, so it's just, you can see any one of these, you're most often going to be seeing the structural formula like this, but you have to be comfortable to know what this means. It looks maybe rather sophisticated, but once you realize what it is, you got this. Okay, so this is two atoms that are sharing a single one pair of valence electrons, right? A pair has two, so it's a single pair, which means two electrons. That's what you see here. So we call this a single bond. It's a single bond because it is one pair of electrons or two electrons. Okay, now is it possible for atoms to share more than one pair with one another? And the answer is yes. And on this slide, the example you see is an oxygen molecule, two oxygen atoms that are sharing two pairs of electrons. I blow it up on the next page, so we'll take a look at it again. But you can have atoms bonded by a double bond, right? So they are sharing two pairs or four electrons. You can have atoms that are sharing three pairs or six electrons. And you have to remember that that both of these oxygen atoms that are sharing these four, it's as if they have the full benefit of the four circulating around them, and same with this atom. So the share is nice because it allows both of these oxygen atoms to fill their outermost shell, which gets filled at 8. Okay, so if we have, so far we've seen atoms of the same element sharing electrons with one another, but lest you think it only has to be between atoms of the same element, I made sure to include the fact that Covalent bonds can happen between atoms of different elements. Oh, please. Sorry, I want to clear my throat. So atoms of different elements can participate in making covalent bonds with one another and sharing electrons. So it does not have to be between two atoms of the same element as you see in A and B here, right? It can be water, that's two different elements. Oxygen is one element, hydrogen is another, or we're looking at methane, right? Carbon with 4 hydrogens. So each one, this carbon is covalently bonded to each one of these hydrogens. So if I showed it to you more like in a structural formula, it's right here. And I'm drawing on top of it now. Right, so there was a covalent bond between this carbon atom and this hydrogen atom, between the same carbon atom and that hydrogen atom, between the same carbon atom and the same carbon atom and that. And hydrogen only needs one electron to fill its outermost shell. Remember, it only has the 1s shell, and the 1s shell fills with 2 electrons. So if hydrogen participates in sharing one pair with a carbon, each one of these hydrogen atoms now has the benefit of 2 electrons basically around itself, circling around itself, so it's nice and stable. Carbon has to have 4 electrons to fill its outermost shell. Therefore, you will find that carbon is usually participating in 4 covalent bonds. It could be a double bond to an atom and 2 single bonds. It could be 2 double bonds. It could be different things. But the idea that atoms want to fill their outermost shell for the most stability, that will dictate how many covalent bonds they might be interested in making, or if they would rather just give up an electron to fill an outermost shell, because it's not likely that they pick up 7. And I'll show you that example as well. So what we learned from this slide, covalent bonds can form between atoms of different elements. You knew this already, but and covalent bonds, there can be more than the sharing of just one pair. We can be the sharing of 2 pairs or 3 pairs. Here's the example of 2 pairs blown up. All right, our space-filling molecule, I mean, that doesn't look much different than hydrogen, doesn't really help us. The Lewis dot structure does, though, and if you look here, you can see that there's two lines between these, right? So not one, because one signifies 2 electrons being shared, and then there you go, there's the second line, so that's 4 electrons, because each line is 2 electrons being shared. So that would mean that each oxygen has a completed valence shell. If we look at this now, it looks maybe a little bit different than we would have seen before, but it's trying to show you all the electrons that are being shared and those that aren't being shared. So this pair of electrons and this pair of electrons, I'll call this, this will be oxygen atom 1 and this is oxygen atom 2. These 2 pairs are not being shared with oxygen atom number 1. They are in an orbital that only, the electrons that only surround the nucleus of oxygen atom number 2. The same with these, right? So they're not being shared, they're paired and not participating in the covalent bond. The ones that are shared, let me erase. The ones that are shared are these right here. Yeah, the ones that are placed between the 2 oxygen atoms. And so if we look over at the electron distribution diagram, that's how it goes. So here's your oxygen atom. How many protons does it have? It has 8 protons. Well, how do I know that? Well, I know that because I can count. I can count the number of electrons. So I know that they need to share, right? They're sharing 2 pairs. So we can also go back and take a look at it here. Maybe that's easier than me chatting about it here. So 8, it's here and it's written, but I could have just counted the number of electrons because you remember the number of protons are equivalent to the number of electrons in an electrically neutral atom. So the first shell, right, fills up with 2 electrons, right? So that's the first shell that we see here closest to the nucleus. And then, so that's 2 of 8, and then there's another 6, and those 6 are distributed in the second shell, right? So I could count them 1, 2, 3, 4, 5, 6. So we know that oxygen needs 2 electrons in order to fill its outermost shell because its outermost shell has 6 electrons and it fills with 8. The second shell fills with 8. So it has a tendency to want to make 2 covalent bonds, whether it does it as we just saw with by bonding, let's say, in water to two different hydrogen atoms, right? So it makes a single bond with this hydrogen atom, and the oxygen makes a single bond with that hydrogen atom. That's a way that it can get to, or it can get to by making a double bond with another oxygen atom, right? So you have basically each oxygen atom and then has the benefit of 8 electrons whizzing around its nucleus. So its valence shell will be filled 1, 2, 3, 4, 5, 6. None of these 6 are shared. That means that they're going to be orbiting and circling around and whizzing around this nucleus only. And then, right, 1, 2, 3, 4, 5, 6. But in the outer shell, it only has these 4. So then it includes 1, 2, 3, 4. Right, 2 were from its own original structure, and now 2 it's sharing from the other oxygen atom. Right? And the same thing, I counted up all the electrons. I said, okay, there were 8 electrons, right, in total, which would mean since 2 go into the first shell, there's 6, right? If you get confused again, you just go back, right? Not to that side, because I won't show you. You go back to this one, you say, okay, 8 protons, therefore 8 electrons. How are they distributed? 2 in the first shell, 6 in the second shell. Second shell fills with 8 electrons, so it needs 2. It's going to get 2 from, in the example I'm showing you, by sharing, right, 2 of the electrons from the other oxygen atom, right? So here, so that's the idea. So it's sharing 2 that came from this oxygen atom, and it is sort of donating to the share 2 of its own. So therefore, each one has the benefit of 8 in its outermost shell. How do I know? Double check. 1, 2, 3, 4, 5, 6, 7, 8, right? Same with this oxygen atom. 1, 2, 3, 4, 5, 6, 7, 8. Now remember, I'm not including the electrons that went in the first shell in counting, because the chemical bonding is based on the number of electrons that are in the valence shell. They're going to be sharing in the shell that is farthest away from the nucleus, that can interact and overlap basically with the electron shell of another atom, right? These 2 electrons that are in the first shell are not participating, right? They are done and they're fine, and that's it. So it's the ones in the outer shell. Okay, so the double bond is the sharing of 2 pairs, not 2 electrons, 2 pairs. And we know that there are 2 in a pair, so it's the sharing of 4 electrons. And that's what you see here, right? The ones that have been put between the 2 oxygen atoms. Okay, now the atoms, though, if they are different from one another, if they are from a different element than each other, they may not attract the electrons to the same degree. So in other words, it's not, if you think about 2 children deciding to share a book, and they're both sitting on the floor, and one wants to read it way more than the other one. The other one's just sort of like mildly interested in the book, whatever it is. And then the first child may grab the book and pull the book closer to them. Even though they're sharing the book, they're turning the pages, together. The one that is intently interested in reading the book may pull the book closer to them. That would be an unequal sharing of that book. Sharing, but unequal. That's the same kind of thing that we have with electrons. If you have 2 atoms and they're not the same, then their attraction for those electrons, their pull on the shared pair, may be quite different. And this is what we refer to as electronegativity. Okay, so I've given you 2 different definitions for electronegativity, and hopefully one of them works for you. They're both fine, they're both perfectly correct, but they're saying what electronegativity is in a slightly different way. And so sometimes one way can help somebody and the other way doesn't at all. So here, this is how I'll describe it. So we're starting with the idea that atoms in a molecule may attract electrons to varying degrees. So they're sharing, as I said, we know this. Look at this covalent bond here and this covalent bond, but do they have the same pull? So here's the first definition of electronegativity. 1, a measure of the ability of an atom that is bonded to another atom, so this is perfectly fine, like this O and this H, to attract electrons to itself, right? So that's one definition. The second definition is the attraction of an atom for the electrons of a covalent bond, right? So both are perfectly fine. So it's how much does this oxygen atom want to pull these shared electrons towards itself? How attracted is it to these electrons? right? And same with the hydrogen. Okay, so now it's time to introduce a little chart. Your book doesn't have this chart, but I find this chart very, very useful, and you'll see it in other books, so I'm going to use it. So here, I put back those same definitions at the top here, what electronegativity is. And so you can pause and read that at any moment. But I like it because it allows you to quantify numbers. Okay, so on our chart, look at this. The greater the atom's electronegativity, the greater its ability to attract electrons to itself, right? So here we have oxygen is greater than chlorine, which is greater than nitrogen, carbon greater than phosphorus, and hydrogen, so on and so forth. So I put a little chart down here that oxygen has more electronegativity, so it attracts the electrons more than nitrogen atom does, which attracts electrons more than a carbon atom does, which I then threw in there is more or less like a hydrogen atom's attraction for electrons of a shared pair. So this is the overall sort of sequence. And we have numbers, and we're going to be looking at what these numbers actually mean. Let me show you. So I just threw this in here because I've seen this, and sometimes this might help. The electronegativity of an atom in a molecule, right, two atoms bonded to one another, is dependent on a couple of things. And one is the ionization energy, and you may have heard this before from chemistry, but this is how strongly an atom holds on to its own electrons, right? Does it want to give them off? Does it want to hold them so tightly and pick up from others, right? So what's the energy basically required to strip electrons from a particular atom? And then the electron affinity, how strongly the atom attracts other electrons, right? So how much it holds on to its own, that's number one, and how strongly it attracts others. Now, if we look at other electrons, if we look at the periodic table, I took a piece of the periodic table to show you once again. If we saw that oxygen had more electronegativity than nitrogen, nitrogen had more than carbon. How do I know this? I'm going back here. Oxygen has more electronegativity than nitrogen. Nitrogen has more than carbon, right? Then the trend for increasing electronegativity is to go in this direction. Okay, so electronegativity increases as you move across a period of the periodic table, right, from left to right. And if you're confused about that, you just go back and you see. Now, you just go back and see this little chart I showed you here, right? So oxygen has 3.5, nitrogen has 3, carbon has 2.5. So let's double check me. Oxygen had most, nitrogen had in the middle, carbon had this. All right, they didn't give you all the elements, but it goes up that way. So electronegativity increases as you go across a period, right? So you go this way. And it's kind of easy to think about in some ways because the electrons are attracted to the positively charged nucleus. And as you go across a period in the periodic table of the elements, right, boron has 5 protons, carbon has 6 protons, nitrogen has 7, oxygen has 8. So there's a bigger positive charge in the nucleus that the electrons can be attracted to. So the more sort of electrons that you have, the bigger the positive pull. So that makes sense, right? Because we know as we move from left to right that each atom gets one more proton, one more positive charge. Electronegativity, if we also look at trends, it decreases as you move down a group. Right, so these are called groups. You can see that here. These are called groups. It decreases as you go down groups. And the reason for that is there's an increase, right? So if you look at, let's say, I don't know, when we look at nitrogen versus phosphorus or something like that, certainly phosphorus has more protons in its nucleus than nitrogen does. But the question is, how shielded are these protons from the valence electrons, which is what electronegativity is talking about. Electronegativity is the pull on those valence electrons. And the idea is that as you go down a column, there are more electrons in shells closest to the nucleus. So those shells with their negative charges are shielding the positively charged nucleus from the outermost shell, right? So if I go, we'd have to go to look at the electron distribution to see this, right? So if we look at something like nitrogen, right, its valence shell, it's only shielded, right? It only has two shells. So that the valence electrons are in the second shell. So the only thing that is shielding the positively charged nucleus from those valence electrons, and these are the ones, any of these would be the ones that would bind, the unpaired ones, um, is just two electrons in the first shell. So there's not a lot of shielding, right? You just have two electrons whizzing around and blocking the pull of the positive charge. If you look at phosphorus, right, while the positive charge is greater here, you have you have the whole second shell that is filled with 8 electrons. So you have electrons that are blocking the pull of the positively charged nucleus on the valence electrons in the outermost shell. So as you go down the periodic table, then, right, as you go down the groups of the periodic table, electronegativity decreases, right, as a trend. It's not that it drops to zero, it's just it decreases. And as you go from left to right across a period, it increases. Okay, so you can leave that in mind. And then I will stop here and I will meet you for the next one. We were on this slide.